Hello. This time we'll look at some oscilloscopes questions at level 3, and some of these can get a bit interesting. Quite a large variety of questions are possible at this level, including this one. Right, now, we're asked for how long it takes this waveform to reach 5% of its final value. It'd be almost impossible to measure that with the time cursors, but what we can do is estimate the time constant and then apply the fact that this is a first order response. It looks exactly like a first order response to work out how long it would take to reach 5% of its final value. For that we need to know the time constant and the equation. Now the time constant is the amount of time it takes the wave to get 63% to its final value. And if we put the voltage cursors on, we can see that the actual, tricky to get these bang on occasionally. There, you can use the up and down cursor keys as well as the sliders to get it spot on the value. Total of 30 millivolt drop. So 63% of 30 millivolts would be 18.9 millivolts. How long does it take to go 18.9 millivolts? That's going to be pretty close. So it's that amount of time from where it starts there to where it hits that value there, which is about halfway up this division. Flip over to the time cursors, move this one to that point there. Once again, you can use the left and right cursor keys to get this. I think it's about there, would be where I'm after. And this one is right at the top there. Well, actually, that's pretty much bang on already. That's 150 milliseconds. So I've got a time constant of 150 milliseconds. Oops. Let's focus that a bit. And the equation for a first order decay response like this is y equals a exponential inverse of the natural logarithm of minus t over τ, where τ is the time constant, which we've just worked out to be 0.15. Now we want to know what value it's going to be to get to within 5%. Well, that would be 5% would be a over 20, because 1/20th would be 5% of the whole step. So I want to know if y is a over 20, then what is t when τ is 0.15? And now it's just a bit of maths on that. The a's cancel out. We can take natural logarithms of both sides, and that would give me minus t over 0.15, and therefore that t equals minus 0.15 times the natural logarithm of 1/20th. Okay, give it a go. Minus 0.15 times the natural logarithm of 1 over 20. Great. Spot on. That's impressive. I'll do a couple more. Try and find an interesting one. Oh, that's reasonably interesting. It's actually, I don't need a piece of paper. I can do that one in my head. The zero voltage level is here, which is halfway up. So this is a square wave, which is either plus 2 millivolts, that's one division, or minus 2 millivolts. Well, plus 2 millivolts squared would be 4 millivolts all squared. Minus 2 millivolts squared would be, again, 4 millivolts all squared. So if I square this waveform, I would just end up with something which was 4 millivolts squared all the time. And the average value of that is clearly 4 millivolts squared. And the square root of 4 millivolts squared is 2 millivolts. It's just 2 millivolts. Moving on. That's a little bit more interesting. Now, I guess strictly speaking, not a question about oscilloscopes, but a question about digital multimeters. But it's set to AC plus DC mode. In other words, this is going to give you the true RMS value of that entire waveform. Right, it's a square wave. Its bottom value here is, I would say, about 80% of a division, which at 100 millivolts per division means that the bottom of this square wave is around about 80 millivolts. The top of the square wave is up here, which I would say is 1, 2, maybe 2.2 divisions above ground, so that would be 220 millivolts. And this waveform is a square wave that's oscillating between those two values. Right, to work out the RMS, we first take these values and square them. So that would be 80 millivolts all squared, which would give me, what, about 1,600 millivolts squared, and 220 millivolts squared. Actually, it would be easier if I did this in terms of volts. That would be 0.08 squared for the 80 millivolts, and 0.22 squared for the volts. And it oscillates between those two. So the average value of the waveform is going to be halfway in between those two. Just the average value of those two. Spends half of its time at that, half of its time at that. The average value of y squared is going to be 0.08 squared plus 0.22 squared over 2. The root mean squared, the square root of the mean of the square value of y, would just be that. Okay, let's see if that works. Square root of 0.08 squared plus 0.22 squared. Need to put all of those in brackets because I want to divide the whole thing by 2, and we get that. Fine, good. Let's see if we can find another one. We've done one like that. Total fall time of this signal. Well, we can use the time cursors here. So if I move this time cursor, say, to that point there, again, using the cursor keys to get it all spot on where I want, and this one down there, 900 microseconds. Easy. This is quite straightforward. It doesn't really matter whether the digital multimeter is set to AC or AC plus DC mode here, because there is no DC content. The average value of this sine wave is 0, because this is the 0 volt point on the scope. So this is a sine wave which has an amplitude of, I would say, about 0.7 divisions. And 0.7 divisions at 5 volts would be a 0 to peak amplitude of 3.5 volts. So the RMS value would be 3.5 divided by the square root of 2, because the RMS amplitude of a sine wave is its 0 to peak amplitude divided by the square root of 2. And here we want percentage overshoot. So, okay, voltage cursors. We can move this one to there, and this one down here, there, and the total is 12.5 volts. That's the total step. If I move this one up to the top here, I can see that the overshoot is 6.38. So in terms of a proportion of the total step, it's that, but we were asked for a percentage, so multiply by 100. Total fall time, we've done that kind of thing before. This is a slightly more interesting one. RMS DMM set to AC plus DC mode for this signal. It's a sine wave, but it doesn't have a 0 mean. If you haven't seen this before, if we have a expression y equals a sine omega t plus b, and that's a sine wave that has a mean of b, not 0. If we ask what is the RMS value of this, we can work it out in a similar way to before. You first square this. That would be a sine omega t plus b all squared. Multiply that out. We'd get a squared sine squared omega t plus 2ab sine omega t plus b squared. And then taking the average of this, Well, the average of the sine squared is a half. That's why the RMS is the 0 to peak amplitude divided by root 2. So the average value of this first term here is just a squared over 2. It's quite useful to know that the average value of sine squared is a half. The average value of this middle term here is 0, because that's a sine wave. It oscillates up and down, its average value is 0, and the average value of the final term, b squared, is just b squared, that's a constant. So the root mean squared, which is the square root of the average value of the square of the waveform, would just be the square root of a squared over 2 plus b squared. Okay, here b is the mean value, and that is 1.5 divisions, so I would say that would be 15 volts. Write that in like that. And A is the mean to peak amplitude of this sine wave, which is looking to me like it's about 0.7 divisions, and that would be about 7 volts. 7 squared over 2. So I reckon the answer should be the square root of 7 squared, which is 49, divided by 2, plus 15 squared, which is 225. Great. And so on. I'll leave the rest to you.